In the last video, we talked about internal energy, the average energy per molecule, and in particular, the connection between temperature and internal energy. That if we measure the temperature that we have measured, at least proportionally, to the internal energy. Now, we'll need to figure out, do we need to take that temperature and multiply it by 3 or what have you, but in some way that the temperature is related back to energy. All right, I will come back and finish that up a little bit because we need to talk about the temperature scale. If the temperature is going to be proportionally directly to energy, then you can't have negative kinetic energy if you have a negative temperature. So we need a temperature scale that's connected back to that, and we'll deal that. It's called the Kelvin scale. In this video, I want to deal with heat. One of the most misunderstood things in thermodynamics. Heat is given the symbol Q in thermodynamics, not H. Sorry about that, but that's just the way it is. And the definition of heat is the transfer of energy due to a temperature difference. So when you have an object over here that's, say, at 300 degrees C, and you have another object over here that's at 100 degrees C, we've already said that the molecules here are not going very fast in comparison to the energy of the molecules over here, or at least it doesn't have the same average energy per molecule, whether that's kinetic, potential, and so forth. We'll talk later on about how I know that there's a relation between the potential and the kinetic. And these guys begin banging around, and energy is transferred, and is transferred from the one that has the most average energy per molecule to the one that has the least. So the energy goes in this flow. That flow is Q. It's energy that's transferred, and the reason it's transferred is it has a different temperature. It's not special energy, it's not different energy. The only real energies are kinetic and potential. It's the microscopic flow of that energy because of the banging around between these molecules, because they're at different temperatures. All right, so the flow of this transfer of energy due to a temperature difference is what we're going to call heat. It is wrong to say an object contains heat. You can't contain flow. The object contains internal energy, potential and kinetic. The loss or gain of energy across this boundary, which I'll mark here and say green, right here where it's touching. The flow of that is what we mean by the heat. Heat is flow. It always has an arrow. It's movement. It's moving. It's not located inside of something. And once it gets into the object, you lose all knowledge of how it got there. So, for instance, think about a river. If you were to, or an ocean, if you were to reach down with a cup and pick up a cup of water in the ocean, you cannot tell me by looking at the water in the ocean if that water got there because of rain, or it got there because it flowed to you from a river, or it got there because somebody poured it in when they dumped a bottle of water over the side of a boat. You have no idea. All you know is it's ocean water now. In the same way, once it gets in the body, it's internal energy, and how it got there, whether it came by heat or we're going to find out by work, you cannot know. Heat is the flow, and we know it when it's flowing, but we cannot tell it when it gets inside. When it gets inside, it's all lost. It just becomes like every other energy, and we call it internal energy. When you have two objects that reach thermal equilibrium, the flow of this energy stops. So heat stops when you reach thermal equilibrium, but when you have thermal equilibrium, you have no temperature difference. Hence, heat is the transfer of energy due to a temperature difference. No difference, no transfer. Now, It feels funny even for me to say heat stops. I want to say heat flow stops. We probably should have always said heat flow and never just said heat. Alright, that finishes this video.